So if
Yeah, sure. So the basic idea is just that we want to check mathematical statements down to the axioms of mathematics, and those axioms might be Zermelo-Finkel set rate with choice, or whatever you choose as your axioms, but you really want to construct these, telephone book scale, deductions right from the beginning to the theorems that you're interested in. And of course, this has been understood in principle to be possible for 100 years, since the work of the logicians at the beginning of the 20th century. But of course, it's pretty far from what you presumably would actually want to do as a working mathematician. As a working mathematician, it's not like in your head you are building long, 1,000 or million long deductions, from the axioms as a matter of regular practice. It's something that you understand in principle to be possible rather than something you really want to do yourself. That's somehow version 0. And then version 1, which has been an active area for the past 30, 40 years, is to instead write computer programs somehow. To do that. So instead of yourself writing the millions of lines of logical deductions, you would instead somehow write computer programs that themselves produce these millions of lines of logical deductions. And these computer programs, or perhaps another way of thinking about it is a high-level language that can be interpreted to the lower-level language, are the way in which people in practice are doing this these days. So this is somehow more what the practice feels like at the moment. People who are interested in this area are sort of working on and developing higher level languages that themselves produce low level deductions of the theorems they're interested in down to the axioms of mathematics. And I think that one interesting observation is that this in itself is still not good enough. So in some sense, when you think about the complexity of mathematics and the way that people are able to keep in their head the mathematical arguments that they're making, one way that they do it is by sort of bundling things inside definitions. So there's this notion of developing abstractions. So at some point, people stopped working with manifolds by saying, I'm considering the following list of 43 charts and the following collection of explanations of how you transfer from one of these charts to another chart. And, the following information on each of the charts and the following check that, this information is compatible between each of the different pairs of charts. And they started working with the abstraction of a manifold to express this notion. So somehow there's the notion of an abstraction that allows us to bundle whole areas of mathematics that are fairly standard inside boxes and only sort of go inside the boxes when it's convenient. Then there's this sort of secondary helper of automation. And good automation, or perhaps good is a little bit too vague, but what I mean is domain-specific automation is somehow the discovery of algorithms, the discovery of patterns of thought that occur over and over and over again, to the point that at some point an expert can tell an expert, oh yes, you prove this theorem by the following kind of argument, and the expert knows what is meant by that kind of argument. A classic example is the notion of diagram chasing. What is diagram chasing? I'm not sure you or I could say, but if someone tells someone else that, such and such is a matter of diagram chasing, that conveys something clear. There is some well understood principle, some algorithm that is going on that could be picked up by one expert and applied by another one without a clear explanation of the details. Maybe another thing is, the notion of a tensor computation. If you tell somebody, another differential geometer that, the way you check some identity is, there's nothing special that goes on. You just check out the computation, you write it out in coordinates and it all falls out. This is again some kind of algorithm that's being described. And there's somehow there's no need to check the details. It's a well-defined concept. So the notion of abstractions and the notion of automation, and specifically this kind of domain-specific automation, I think, are two of the kind of higher level principles that you start to see as people make sense of writing computer programs to do mathematics. And they're also, I think, what you see when a mathematical field becomes more mature and people start to really, try to write down in textbooks and as expository articles and for outsiders what's going on in that field. A mathematical field gets to a certain point and you start to see these kinds of things coming up as part of the standard package of that field as it's expressed to outsiders. So both of these come with maturity to a mathematical field. And I think the interesting point is that they also become the crucial mechanism by which it becomes possible to write up in computer language a mathematical field. Because sure, you could write, a million lines of code to check a mathematical theorem, but nobody would understand it. And so if instead you can write suitable abstractions in your code and suitable automation in your code, you can end up with something that will, on the one hand, unfold where needed to a full down to the axioms check of the mathematics, yet at the same time can be understood at a high level and believed at a high level by human beings. So in this talk, I want to talk about the current status and some of the challenges and prospects of formalizing being the word for this process of writing in computer language mathematics. So the process of formalizing differential geometry, which is the area that I myself am trained in as a mathematician. And I want to give sort of a sketch of what people have done in the last 5 years since this started, and follow up with some descriptions of two of my own projects. One which is really a kind of abstractions project, and one which is a kind of automation project, in order to express these points of where I think work is needed to keep on with this task. So I would date the beginning of attempts to write down differential geometry in computer theorem provers to 2019. So the first work I know of in this direction was done by Imler, and Bopajan. Fun fact, Bopajan and I were in the same year as graduate students at Princeton. He was a low-dimensional topologist. I was a geometric analyst. Neither of us knew that we would get seduced by this new area at different times and in different languages. But anyway, the first work was done by Bopajan and Flavia Imler in 2019. And this was done in the language Isabelle. And so what they did in the language Isabelle was to write down a definition of sort of real smooth manifolds. Somewhat along the lines of the standard definition that you'll see in an undergraduate textbook. So a manifold is, a collection of charts, each modeled on a small piece of Rn, and here are the transition functions. And together with this definition, I think they may have done some associated things like defining what a smooth function is. And they also did a couple of examples. So they did the example of the sphere. They did the example of projector space. And so this was done in the language Isabelle, as I said. And this was a tremendous amount of work, very impressive. They also, I think, somehow at the end of this project, expressed in their paper about it, that they were somehow pessimistic about the prospects, that they'd found a tremendous amount of work. They were sort of a little bit frustrated by what they were, how far they got. But I do want to sort of underscore that this work was done by them as a sort of proof of concept of taking the textbook definitions and really trying to translate it directly. So about the same time, finishing a bit later, so Sebastian Grosel started writing down theory of manifolds in Lean. I'll call that sort of 2019 to 2020. And maybe this is a bit earlier, maybe this is more like 2018 to 2019, given that it was published in 2019. And so Sebastian took somehow almost the opposite approach to this. So somehow he started from the very beginning to think of all of the various various generalizations that you might want along the way. And I'll talk about some of them later on, in order to sort of avoid the problem that I think is implicit in this kind of work, which is that if you build a theory and it's a ton of work, and then all of a sudden you need complex manifolds, or manifolds with boundary, or infinite dimensional manifolds, or orbifolds, or any of these other related concepts, if you don't bake it in from the start, you might well find that it's not there when you need it. So I would say that Gozel's approach was almost the opposite approach. Like, you know, it really was sort of think from the beginning about all of the complexity that might be required. And I'll talk more about that later on, but in particular, the generality that he covered was the sort of traditional Kobayashi and Mizu kind of approach of like structure groupoids. And the notion of a model space together with a certain collection of partially defined functions between regions of that model space, satisfying that it's closed in a certain sense under composition and under inversion and so on. So this very general notion of structure groupoids, which contains as examples or perhaps the canonical example being, you know, this smooth and holomorphic so in the sense of, you know, somehow the groupoid consists of, let's say, Rn together with the smooth functions from parts of Rn to other parts of Rn being a specific example, and then somehow the general notion of a space equipped with parts whose transition functions lie in a given group. So I will return later in the talk to some of the reasons why you would want to do this, but let me try to already hint at somehow why you would want to do this. The issue is the following. On paper, for example, people who work in complex differential geometry very often want to consider something that is a complex manifold, and then sometimes they're like, oh yes, and just temporarily I want to consider this as a smooth manifold, a real manifold. Or equivalently, they're working on something which is a real manifold, and they want to temporarily consider it as a topological manifold, or only consider its CK structure, or they want to work with a manifold whose transition functions are conformal functions, and then to temporarily, you know, drop that conformality structure and consider it just as a smooth manifold. So how can you keep somehow in the package at the same time the ability to consider an object as all of these different things at once? This is the basic problem that somehow was circumvented in the Isabelle work by really only fixing one point of view, the point of view of real smooth manifolds, and forgetting that many of these might come from other places and you want to consider these different points of view. So the approach taken by Sebastian and continued since then in Lean is that you want to take this space equipped with charts as one basic notion. And in a sort of standard Lean distinction, this is the data. And then there are the properties. You know, it could have the property that its transition functions are smooth, lie in the smooth groupoid. Or it could have the property that its transition functions are holomorphic, they lie in the holomorphic groupoid. Or it could have the property that its transition functions preserve orientation. Or it could have the property that its transition functions preserve CK structure or conformal structure or whatever. And the point is that since all of the sort of higher level things are just properties, you know, many of these properties can coexist on the same basic object. And you can have a whole network of implications that, you know, if the transition functions have the holomorphic property, then they also have the smooth property. And if they have the orientability property, then you can also forget about that temporarily. So this distinction between the data and the properties is a very common approach in computer formalization to avoid headaches that don't even exist on paper. So I'll be returning to
the request to
Oh, yes.
larger than that in the future. So those last lines are maybe.
Oh, these ones are too small. Okay, yeah, thanks. Okay. So just to sketch how far that initial development by Sebastian went. So it also got as far as, so the construction of the smoothness of maps. And smooth functions, and it got as far also as, so I should even say that, so the group weights here that were involved were also general enough to deal with manifolds with boundary, so smooth, relative to a set, relative to an octant, let's say, or an, an n-dimensional octant. So somehow the notion of having a boundary was built in. They were in principle Banach manifolds also, so a lot of theory was done in this generality. So there's no need for future work in the infinite dimensional setting. And then there was somehow a backdoor definition of the tangent bundle, not somehow as a vector bundle, because that hadn't been defined yet, but in some weaker sense, just as a kind of object. And I'm sure I'm forgetting some things, but already in this initial development, it was a ton of work, and I somehow think it's a very beautiful development that sort of contained a whole theory and a whole sort of philosophy for how the future development should go. Okay, so I want to sketch some of the things that have been done since then in Lean by other people, sort of working within this framework set up by Sebastian. So there was some work of Anthony Bohr, and Niccolo Cavallari in 2021, defining Lie groups again within this framework. So Yuri Kudryashov in 2021 proved the Whitley embedding theorem. So this is the topological theorem saying that a manifold can be embedded topologically in a sufficiently hard Rn, not the later Nash embedding theorem saying that it can be embedded in a metric preserving way. So somehow this is something that can be done sort of just by constructing good enough partitions of unity and gluing them together on a sort of sufficiently, large enough collection of copies of Rn produced by these partitions of unity. Then there was the sphere version project. So led by Patrick Massot, which proceeded in a couple of parts. The initial part being a manifold free part that was completed in 2023. So sphere version being the differential topology theorem that a sphere can be turned inside out by a smooth homotopy in Rn, in R3. And so there was a somehow manifold free part which just used the, I guess, the sort of H principle in a kind of Rn sense. So this was completed last year by so Floris van Doorn and Oliver Nash and Patrick Massot. And then there's a part which was completed to a first approximation at the same time or a bit later. Maybe I'll call it 2022 to ongoing, which is to translate this into the language, the full language of differential geometry in Lie. This is somehow completed in some sense, but still modulo somehow an imperfect definition of fiber bundle, which we're working on. I'll say more about that later. And then, I don't think I even have space for some of the other projects that maybe I'll mention them verbally. So there was work by Winston Yin last year doing the existence of integral curves on a vector field, some work by Michael Rothgang proving Sard's theorem, and work by Sophie Morel, which constructed the manifold structure in this sense on RPN. I myself had earlier done the manifold structure on a sphere. So as you can see, where all of this work has got to at the moment is the contents of your classic, textbook on smooth manifold theory, without even trying to get into what we actually call differential geometry. The Riemannian metrics, the symplectic geometry, the vector bundle theory, like all of this sort of the stuff that feels more geometric as opposed to manifold theoretic. has almost as yet not really come on the horizon. But nonetheless, I think there's been a lot of work going on and a lot of ideas that are already sort of there and can be discussed and thought about. And I want to go into a couple of my own projects that I think exemplify some of those ideas. Maybe I'll pause briefly in case people have questions about what I've discussed so far.
The question is something like a sphere version, is some part of that going into math world? I mean, is all of it?
Yeah, so I would say at the moment, it's a little bit sort of this issue that I mentioned, and I'll get more into that in the next part of my talk about sort of somehow feeling that parts of it are written using not the perfect approach to differential geometry, have put that on pause because the maintainers of this MATLAB library that I am one of the maintainers of. So we sort of tend to sort of have more of a feeling that it should be a mature development of theory that makes it into the library, as opposed to like somehow a sort of a bit of a shortcut. So it's been held back sort of by the feeling that parts of it are done by what you might call a shortcut.
Okay.
But I would certainly imagine.
I guess the question, I don't have a long discussion, but there are two parts, and the one is what you were just saying, that there's a standard, and then the other is that sphere version itself might be considered a very special kind of result. Do all results and papers within MATLAB eventually, or is like they become too special?
Well, I think that sphere version would definitely make the cut, right? Like, I mean, mainly because sphere version itself is like a relatively short consequence of much more general stuff. Like somehow, you know, it's such a short consequence of such general theory that it clearly deserves to be in a canonical library that you might as well include the application as well. So I want to talk about two projects. And the first project I want to talk about is a project of my own on constructing vector fields. So this is a project joined with Floris van Doorn. So this is Fordham. And I would describe this project as an attempt to carry out somehow the philosophy that I was explaining in the case of Gozel's work on the construction, the definition in a formal sense of smooth manifolds, also in the case of vector bundles. So again, you want to ideally achieve the same result, that you have a theory which can be instantiated in many different settings, for smooth vector bundles, for holomorphic vector bundles, for topological vector bundles, for all sorts of other things, in a way that makes these transitions as transparent and as seamless as possible. So let me spend a few minutes talking about what I would, you know, just to refresh the audience, who I assume are not all differential geometers, like of what a vector bundle is. And then I will talk a little bit about some ways that you might take to write them down in a formal language. So what is a vector bundle? Well, it's so you have what we call these space, which I'm describing as this purple line, you know, some manifold. And then you have above that a collection of fibers. And each of these fibers is a copy of Rn, and the idea is that they're sort of bundled together in a way that is, you know, imagined to vary smoothly from point to point, so that there's a notion of smooth manifold structure on the whole thing. So, you know, you could say, you know, you could take that approach as a primary one and say there's a manifold structure on the whole thing, and it also happens to decompose in this way as a collection of fibers which are themselves parameterized by some other manifold. Or you could do it, you know, in some other order and take as primary the base space and the fibers. But this package of things is what constitutes a smooth manifold. So let me try to write, maybe I'll introduce the terminology. This is like E sub X, E sub Y, etc. So some components of that definition. And what I'm going to try to explain is somehow that the package that we have in our heads when we think of what a smooth vector bundle is, like actually contains many things, many things that are more than somehow the straight definition, that we have in mind like a whole host of things that are as being part of the definition, together with a whole host of compatibility conditions among those different things. And that any sort of true definition would probably have to pin down some subset of the things as being the primary notion and say that the rest are constructed from those primary notions. But the choice of what within the package to treat as the definition, has some subjectivity to it. So here are some of the things that in the head of a differential geometer all form part of the definition. So there is this base space. And there is this so-called total space. And there is a notion of this projection. From the total space to the base. So this whole thing being the total space, there is this notion of projection, which sends anything on this fiber to that point, sends anything on this fiber to that point, and so on. There is the notion of the fibers E sub x for x in the B, the base. And the compatibility condition that these are equal to the inverse images of that point into the projection. So that if you imagine taking the disjoint union, which I'll write sigma following Lie notation, this disjoint union over all of the points in the base of the fibers is equal to the total space. And there's the question of whether this equality is even a well-typed equality, and if it's well-typed, whether it's by definition or as a consequence of something else. But if I put this equality in quotes, that's probably good enough for now. And then there's going to be also, as part of the definition, or perhaps not as part of the definition, a structure of a vector space on each of these fibers. And they're all isomorphic to some fixed F, which is the model fiber. And then again, you might consider this as part of the definition or not, the notion of local trivializations. Are maps from portions of the base of let's say E from the inverse image under the projection of that to the U cross the F. So that's fixing some little portion here and taking the associated fiber collection that lies above it, like here, and identifying that directly with a product of the base across the model fiber. And these should be respecting the projection, and they should also be what's called fiber-wise linear. That is, if, okay, yes.
I have to ask because of your emphasis on the obvious questions of why not first fiber bundles and then vector bundles, and why not singular fibers?
We'll get there. Okay. Yep, and then finally somehow a compatibility notion that Okay, so given two trivializations, there is going to be this notion, so given E from one of these portions, inverse image of pi to U cross F and inverse image of some V to V cross F, there will be some notion of a transition from, I'll call it phi, from the intersection of the two into the endomorphism space of F. Okay. So I think, you know, I certainly see some differential geometers in the audience, and maybe I don't need to expand too much, maybe just for those who are not, maybe a couple of standard examples. So one standard example is if I have the circle, then I can have the cylinder lying above that circle, it's a vector bundle. So this is a vector bundle of rank 1 in the sense that it's modeled on a one-dimensional vector space. And then maybe a second example is that although it's a little bit harder to draw, you can consider the Mobius band. So how do I draw the Mobius band? Let me attempt. All right, so imagine that this is somehow only a portion of the Mobius band, and all of these lines actually go off to infinity. This can be considered as, again, a one-dimensional vector bundle over the circle expressed inside it as that blue notion. But by contrast with the cylinder here, this one is one that really uses the full flexibility of the notion, in the sense that although there is a local trivialization near any point, which identifies a little portion with a box, it cannot be globally expressed as lying across the circle. It's got a different global topology. Is that a question?
Yeah, I should have asked this question of your manifolds, and it applies to both, which is that when you propose a manifold with a set of charts, and then you talk about two manifolds being isomorphic, you want to handle, like, you know, two different sets of charts, say, on the same manifold that's still isomorphic. How do you do that?
Okay, so I feel like I'm still in the math, but let me now move to the question of what you write in order to do this. In order to do this in a theorem.
But you can get there.
Yeah. But so I think there is this notion of what is part of the definition and what is like a theorem, or what is like an auxiliary definition from the first definition of a vector bundle. And then the notion of what is equal is also a simple question, as you're already pointing out. So, I mean, there's a whole bunch of theorems you could prove about vector bundles. Like, I think, you know, vector bundles turn up as the tangent bundles of manifolds, and so you need them to do, you know, Riemannian geometry, symplectic geometry, the whole shebang. There are also intrinsically interesting, like, topological theorems about vector bundles. You know, you can do characteristic classes, you can do stability theory of vector bundles. And then I think it would be really nice also some, you know, probably not too far away also to have like the Picard group structure, the group structure on the collection of vector bundles on a space, and things like that. And then finally, like, so as we've been discussing, all of the same questions that came up for manifolds also turn up for vector bundles, in the sense of, you can do all of this, and, you know, I've written down these maps, but you can say that these special maps, like the trivializations and the transition functions, should be smooth, they should be continuous, they should be holomorphic, etc. You get different notions depending on the category that you're considering the basic functions as belonging to. So there have in fact been 3 different definitions of vector bundles in MATLAB, and MATLAB being the leading mathematical library, and I want to walk you through somehow what was done for each of these definitions and why it was scrapped in each case and replaced by something else. Because I think that this is a good somehow case study in this kind of mathematics. So there was a first definition of topological vector bundles in March 2021 that was done so by Niccolo Cavalieri and Sebastian Guazel. And at this point, I think one of the motivating ideas they had was that Sebastian had already written down like somehow as an object the tangent bundle, but there was no notion of the vector bundle structure that it was supposed to carry. So you wanted at least to have a definition that was good enough that the existing tangent bundle did satisfy it. So one of the interesting ideas was that, so connected to what you had asked about why not include fiber bundles. So one of the interesting ideas was that you could consider this total space as being part of the definition of a vector bundle. But you might make your life easier if you don't. So imagine that you decide not to include this total space as a component of the definition. Then instead what you can include as data is the base space together with a family of fibers indexed by this base space. So you're going to have a family of vector bundles, one for each element of the base space, and you will then make this a definition right to left. Oh, sorry, left to right to left, and that E is defined to be this disjoint union. So this was controversial. I think it was the right call. So this is one thing that they got right, and I want to briefly explain this. One reason it was controversial is that people who were interested in fiber bundles found it unpleasant, for example, that, later on, for example, if you were thinking of the Hopf fibration, for example, which is a way in which the sphere S3 is a fiber bundle over the sphere S2, that this would not, necessarily be a bundle according to this definition, or perhaps maybe another example is if you take the Iguchi-Hansen manifold, which is it's a vector bundle of complex rank 1 over P1, this thing could not literally be a vector bundle according to this definition if you start with the manifold itself and try to say, okay, and inside of it there is this structure of the fibration. So it was controversial to people that objects that they thought of in their head as being vector bundles would not be literally vector bundles according to this definition, but would just have the possibility of being equipped with maps to a vector bundle according to the strict definition that preserves certain properties. Nonetheless, it was chosen as part of the definition to say that vector bundles have this disjoint union structure baked in, and I think it was the right decision. For various reasons, and maybe one of them I will mention. The one being somehow that if you want, so if you want, for example, to work with aspects of the vector bundle structure on the fibers, it can be quite awkward to have to work with them primarily as objects which are inverse images of certain maps by certain points, that somehow keeping this in place as you try to add and subtract and scalar multiply things can be quite painful. So somehow by baking in the algebraic structure of the fibers, you avoid that particular difficulty. But this is a trade-off that you raise the point of fiber bundles doesn't have an obvious payoff in the sense of, in the case of fiber bundles, because in fiber bundles, you aren't trading off the ability to work algebraically with the fibers with the topology of the situation. There's only the topological situation. So this is a case where somehow the trade-off that worked for smooth bundles was not obviously a good one for fiber bundles. So in fact, at this stage, it was a trade-off that was made for vector bundles without any associated notion of fiber bundles, which caused problems later. Okay, so the second idea, so the first idea being that you remove this from the core definition. You instead treat it as a secondary property. So the second idea was the idea that being a vector bundle should be a property, in the sense that if you have this index family of vector spaces and you have a topology on it, it should be like a fact you can check, like a yes/no property of the existence at each point of a trivialization. And I think this again was a plausible idea, but as I'll explain, it turned out to be misguided. So the idea is that, sorry, yes.
You just take P
So the topology. Right, so this was still only a definition of topological vector bundle. But it's, I mean, even at the level of topological vector bundles, this still had some problems because, you know, you can say, okay, it's a disjoint union equipped with a topology, and the topology has the property that near each point there exists a trivialization. So this is quite flexible, but it turned out not to work. So the reason, as was subsequently discovered, that this doesn't work is, I mean, has anyone here like read, like, for example, Lang's book on Banach manifolds and, you know, setting up infinite dimensional manifold theory? Lang doesn't follow that definition, and it turns out that there's a very good reason, which is that in infinite dimension, you know, I knew nothing, you know, about infinite dimensional manifolds until I started studying this, but in infinite dimension, it turns out that, you know, if you have this setup, and you're trying to make this smooth theory, there, well, even without the smooth theory, even if, for example, you're just trying to define, you know, stay within the class of topological vector bundles, but you want to define, for example, the dual bundle of a vector bundle, like somehow this property of the existence at each point of a trivialization is not good enough. Like, it turns out that, you know, you can have, like, you know, the collection of all the trivializations that are suitable, and they're actually sort of not compatible with each other in the sense of admitting valid transition functions, which in infinite dimension probably means that the transition functions lie in, like, sort of the space of continuous linear maps and very smoothly with respect to the operator normal match. So it turns out that a subtlety well known to infinite dimensional manifold people, less well known to the rest of us, is that part of the definition in infinite dimensions should be this particular choice of a collection of trivializations of your vector bundle, which covers the whole vector bundle and which are all compatible with each other. It was actually a strict subset of the collection of all trivializations. So this was, like, I think, an interesting case study of the fact that if you try to set up with optimal generality, you can make mistakes if you fully know the details of the generality involved. So I guess maybe the short version is that there was an attempt to make somehow this part not fully part of the definition, but just somehow an existential, and that was misguided. Okay, so that was version 1. Version 2 was made by myself and Patrick Massot about a year later after we tried using this definition to define the topological dual of a topological vector bundle and hit exactly this problem. So at this point, we changed the definition to bake in a particular atlas of local trivializations for a vector bundle. So this property here became reinstituted as part of the core definition. And I think this is quite ugly to people who are classically trained in differential geometry. It feels ugly to have to choose an atlas, like we're used to all working with the maximal atlas all the time. And it seems very unpleasant to bake in that choice. But anyway, yes, we baked in the choice. And this made it work. But this is still only a definition of topological vector bundle. And 6 months later, when we tried, so 6 months later, Floris and I, so this is in late 2022, decided to try to define smooth vector bundles. And we realized that the existing definition that I've explained to you of topological vector bundles was not good enough. So let me now try to explain why it wasn't good enough. The idea we had in mind was that there was this perfectly good definition of topological vector bundles, and we were going to define smoothness as a property that a topological vector bundle would have. So smoothness in the sense that, for example, if you cook up these transition functions here between two given trivializations, so this should be as smooth as a map from U intersect V, which lies in the base manifold, to the endomorphisms of the model fiber, which is itself a manifold. So this was our idea of how to define a smooth manifold, and it was somehow not good enough. And I want to try to get at why this was not good enough. Maybe while pointing out that somehow the basic problem you're trying to solve with things like this is you want it to be such that the stuff that's sitting around has its own existence, and then you can talk about smoothness, talking about being holomorphic, whatever, all as properties that may or may not exist on the same basic object. Yes.
I mean, the basic comment there is it can be one topological manifold with several smooth structures, so you have to represent that.
Yes. Yes. Yes, yes, yes. So, okay. Okay, so here somehow it is, okay, so you would like it to be the case that a smooth vector bundle is a smooth manifold, and you would like it to be the case that a complex vector bundle, a holomorphic vector bundle is a complex manifold. And if this doesn't sort of fall out immediately from the definitions, you sort of failed. Like this is a basic theorem that you would like to be true. So, okay, so what is the problem? Let me maybe erase some of this and we'll just keep it in our heads and try to explain it. It's that if you have holomorphic vector bundles, you can make it into a real manifold in two ways. You can say, okay, this is a holomorphic vector bundle. So in particular, it's a complex manifold. And so in particular, it's a smooth manifold, like real smooth manifold. Or you can say it's a holomorphic vector bundle. So it's a real smooth vector bundle. And so in particular, it's a real smooth manifold. And I think any differential geometer would say to you, it's obvious that you get the same manifold, no matter which of these two constructions you take. But what does it mean that this is obvious? Like, how can you ensure that, you know, somehow you don't have to like manually prove that you get the same manifold when you take this approach both ways? You know, or if you do have to manually prove it, maybe you would think, okay, I'll make that sacrifice, but then how do you avoid having to transfer, like, you know, take results proved by this approach and transfer them all back over to this approach whenever you want to use it in practice? So the question is, how can you set up the theory in such a way that somehow it is by definition the same real smooth manifold, no matter which path you take? And the problem is the following. So what is the data of this real smooth manifold? It is the collection of charts. So the charts that you have on this real smooth manifold. And what are these charts? Well, the way that you would get the charts from a holomorphic vector bundle is you have these trivializations sending portions of your holomorphic vector bundle to portions of the manifold across the model fiber. And then you combine those with, so here's the manifold, you combine that with bits of chart on the manifold to send this part here to the model space of the manifold across the fiber. So these are obviously the objects which should constitute the charts for this thing, considered both as the smooth manifold via this path and as the smooth manifold via this path. But what that means is that you need to ensure that if you, for example, are making the same object into both a real smooth vector bundle and a holomorphic vector bundle, that somehow you choose the same trivializations of the vector bundle both times, while just, you know, noting different properties the first and the second time. So in some sense, you need to back all the way up and consider the choice of trivializations as canonical to the construction of the vector bundle, even be either a smooth or a holomorphic vector bundle. In fact, you need to bake in this choice of charts, which I've explained was necessary because of infinite dimensional concerns for vector bundles, actually into the choice of fiber bundles as well. So again, this was controversial, like people who were topologists and primarily wanted to work with topological bundle, you know, topological fiber bundles, didn't like being forced to pick for forever a choice of charts on their topological fiber bundle right at the beginning. But it turned out that this choosing the charts down at this level was the only way to avoid getting this kind of diamond. Okay, so I maybe will defer any further discussion of that to the questions, because I wanted to mention for the last 3 minutes of my talk, somehow the other kind of problem that that I wanted to mention. So this first one, I mean, just to summarize this discussion, what was going on there was somehow this is an abstractions problem. Like the Kobayashi-Namizu stuff, like, is fairly well known as a sort of suitably general approach to smooth manifolds. But I think the sort of analog of this was not, as far as I know, done by Kobayashi and Namizu. And it's not a terribly surprising story to most differential geometers, but I don't think it's been written down before. And so I think the upshot here is that there's a lot of sort of like Bourbaki style work to be done in all areas of mathematics and coming up with the abstractions that work to make the obvious things obvious. So the second point which I'll exhibit just briefly is, here's a sample proof. And I want to briefly discuss, so this is a second task, so automation for inequalities. Work with Mario Carneiro at Carnegie Mellon. And so here's a sample proof. It's the proof of Minkowski's inequality. Doesn't on the surface have anything to do with differential geometry, but anyone who's done any amount of PDE theory on manifolds knows that somehow this kind of argumentation is ubiquitous there. So I want to prove, you know, for any given p greater than equal to 1, if I take the LP norms, I have that the LP norm of f plus 3 is less than or equal to the LP norm of f plus the LP norm of g. Okay, so triangle inequality for LP functions, basic result in geometric analysis, you know, typical of many other arguments. So let me give you a proof. I can say that the LP norm of f plus g to the p is the integral over my space of f plus g absolute value to the p. And I can split this as f plus g times f plus g to the p minus 1. And then I can say that this is by the triangle inequality less than or equal to the absolute value of f plus the absolute value of g times f plus g p minus 1. And then this can be split out as integral of f plus g to p minus 1 plus integral of g, f plus g, p minus 1. And now I can use Porter's inequality on each of the two pieces. So this is less than or equal to the integral of f to the p to the 1 over p integral of f plus g to the sort of 1 p over p minus 1 times p minus 1 to the power of 1 over p minus 1, I think, plus the same for g. And this boils down to the norm of f in the p norm, and the same one neglected becomes the norm of g in the p norm, all times the norm of f plus g in the p norm p minus 1, cancel the common factors of p minus 1 on both sides, and we're left with the inequality. So classic proof, you know, like there are millions of proofs like this done by every geometric analyst every day. But the point I want to isolate, and that Mario's work with me is addressing, is how do you carry out steps like this? And steps like so in both of these cases, what happens is that you have a well-known result. In this case, it's the triangle inequality pointwise. In this case, it's Holder's inequality, and it's being applied to a piece while keeping the rest of it constant. So here you have a well-known inequality, you multiply it by something, you integrate that. here you have a well-known inequality, you add to it another well-known inequality. So what's going on here is a kind of congruence theory for inequalities. Like we all know that it's not in general true that if you have an inequality, you can multiply through by something else and you get another inequality, but it's true under reasonable conditions. You know, it's true that if you multiply an inequality by a positive number, then the inequality is preserved. It's true that if you, if you raise an inequality to a positive power, then the order of the inequality is preserved. And so people write this kind of thing. It's the standard currency of geometric analysis, like, and many other fields of mathematics. And they know what you're supposed to be checking along the way, to an extent that this proof requires no annotations about, and the factor is positive, and that's why that's okay. So we've written some automation that does this kind of thing. It picks up, it does the obvious thing in every setting. But what I think is interesting is the fact that it was not previously necessarily observed that when people write proofs like this is what they mean. And somehow writing the algorithm that picks this out and identifies it is somehow, again, part of this meta-mathematical work of understanding why mathematical proofs can be relatively compact and what they expand to and what the algorithm is. Okay, I'm over time. I'm sorry to keep you all.
Thanks, Heather. Great talk. I really feel we know something about what one has to think about to use lean. Are there questions from the audience? Please.
I think that general beginning the sort of mathematical community, you take the proof, you kind of reduce it to a complete phone book size check of all the details. And here you have a few different definitions for vector bundles. Is it all theoretically possible to create that phone book, but just not practically, like the computer code would be awkward, or do you just see unintuitive? Is that the challenge here?
So, I mean, when you've done something in lean in a sort of higher level language, you can certainly expand it to the phone book. There are tools to do that. I've done it once or twice just to convince myself, but I've never looked at it again. But you're saying, is your question whether it's possible, or whether somehow, whether there would be any advantage, like whether if it were possible to create the phone book without these sort of abstraction tricks, whether it would be worth doing it? Is that sort of your question?
No, more would it be theoretically possible? I guess in normal mathematics, we would just say, well, the phone book exists. We would literally never create it. And maybe my question is, for all three of the definitions you gave of vector bundles, is it pretty clear the phone book exists? You could do this, but the question of choosing the right one or boxing style is to find one where not only does it exist, but the computer can do it efficiently.
All of these definitions, somehow the reason that we moved away from the two first definitions to the later definitions is because people trying to use them in practice encountered certain problems. So it wasn't that the definitions themselves, were bad when expanded to the phone book. It was that anyone trying to use them for other things realized they would need 10 phone books rather than one phone book to keep working from there. So somehow the usefulness of a definition, the sort of the correctness for these purposes of a definition is proved by whether it makes the subsequent work on from that definition easy or not. And even though always subsequent work using this definition is going to be phone book scale, there's still a question of whether it's many phone books or one. And I think that's the distinction that's being made here.
Well, let me ask a different, closely related question. I'll speak into the microphone. So it may be the case that for some concepts, there is no one best definition. I recall that for matchwords, there are 8 definitions that each have their advantages. And so how would you decide if maybe there's a concept that should have more than one definition in MATLAB? And is it really sustainable for a single group of deciders to decide such things?
This is a great question. So I think, and in some sense, I probably already hinted at this when we were talking about how the definition that we came up with for vector bundles made the people who really only wanted to use fiber bundles a little bit unhappy. I would say that one thing that has changed my thinking in the last 5 years since I started working with formalization more is believing more than I previously had in the existence of canonical choices and canonical paths, in the sense that I would have been really dubious 5 years ago that there was a way of doing things that was right enough to work for many people's purposes. And now I still like you, sort of have some doubt about this, but I think in more cases than I previously thought were possible, there is a good choice that works for everything. There is a good abstraction. And I think maybe I would pair that with the acceptance that in some cases you do need multiple points of view. Like maybe a good example would be if there are two generalizations growing out of some basic theory. And, people think about the basic theory in both ways, and you just actually need in the end both of those standard generalizations. And they're completely different standard generalizations of the same idea. And you do want to have both of them. And then the question is, so, what does the really simple example get? And maybe you do need like the two big generalizations in the dictionary between. So I think, yeah, I think these are questions that are very actively grappled with. I think
So,
that
but it sounds like you're more on the side of that there are centralized, better decisions that can be made in a more centralized way. And
so
as the community grows, it's not, obvious.
I have been impressed by somehow the dialogue that happens among people who come from different areas, and somehow the ability of this dialogue to produce a suitable notion that works for a lot of people. I've been impressed by how often this has been the case. And I think the point about the community growing is an interesting one, because at the moment this is happening in a community that is small but does contain people from different areas. So I think there's a real question here, and I would say I'm still somewhat bullish in the capacity of mathematics to come up with perfect generalizations for perfect use cases. But I agree, it's a real question.
Thanks. Other questions from the web, the Zoom audience? I think we can.
I'll ask a question. I think I heard you at some point talking about making things that are obvious to mathematicians more obvious to the machine, making obvious things obvious. My question is about the foundations, dependent type theory. So just as a point of contact, in 1995, there was a paper proving a groupoid interpretation of type theory in general. So you mentioned some groupoids. So the question is your experience with lean suggesting anything in the way of lean development, anything in the way of general foundations for mathematics and dependent type theory? Are people, is there some way, the question is also related to automation. Are we going to set up benchmarks? I'm an AI person, and in AI, people always set up benchmarks and evaluations. Is there some plan to develop benchmarks for levels and effectiveness of automation techniques? So the question is about, what are we learning about lean?
So the question of foundations is one that I'm not sure I'm equipped to address. I'm not a logician by training, and I would say it's really remarkable how little you have to know about dependent type theory to formalize mathematics. So I would say really, mathematicians for a long time have worked far from the foundations. They know they exist if they need them, but they don't tend to look into them. And somehow, I would say it's somehow a success of the abstractions before we got to vector bundles, a success of the abstractions surrounding, the real numbers and topological spaces and Banach spaces and so on, that I sort of never needed to look inside those abstractions, on a regular basis enough to hit against the dependent type theory. The question of automation and benchmarks is a really interesting one. So one point of comparison that I'll throw out is that I know that something that was influential for computer scientists, who were, of course, the pioneers in formalization, was that about 20 years ago, and I don't know the area well enough to be able to name the people, some group of people put out like a collection of sort of standard problems that ended up being like quite influential in the development of proof assistance for proving things about programming languages. They put out like a list of 10 or 20 problems. My understanding is that they were all on the scale of things that like a graduate student could do in a couple of days. And as people invented new languages and new systems, they would implement in their new languages and new systems their solutions to these standard challenge problems, somehow exhibit how their way of doing things made this particular well-known standard problem easier or not. So I really like this idea. I can look up, if you're curious, the name of this group of challenge problems that became so influential. But I think something like this could be a valuable addition to the mathematics literature. And as far as I know, it doesn't exist. Like somehow a collection of problems that showcase some of the difficult points of formalization and allow people who think they have a really great idea for solving a particular problem to be able to argue with data about why it's easier. In terms of automation more generally, so one thing that I really am optimistic about is domain-specific automation. So of course, there's tons of work on very general automation, sledgehammers and SMT solvers and neural networks and so on. And personally, although I admire this work, the work that is closest to my own heart is domain-specific automation, like the kind I sketched out here, that identifies a particular kind of argument that mathematicians in a particular field make again and again, and explains what is algorithmic about that. So I think it's hard to set up a benchmark because the problem is not writing the algorithm, it's identifying that the algorithm exists in the first place. But, you know, as perhaps a particular example, you know, once Mario and I realized that this was a standard kind of automation, you know, in the last 6 months since it joined the library, it's been used hundreds and hundreds and hundreds of times. Like it really turns out to be something that we do all the time. We just haven't realized it was part of our grammar. And so I would frame this as conceptual rather than quantitative work. I'm not sure what the benchmark would be, but it's an interesting question.
Thanks. Nice talk.
More questions? Questions here, questions from the Zoom audience? Please. Repeat this question. The question is if algebraic or other forms of geometry are easier to formalize than differential geometry.
Okay, so I wouldn't say it's easy. I think, you know, there are particular problems that differential geometry has just because of sort of all of the analytic questions that are not there in the case of algebraic geometry. So in the same way that there's like this handful of people working on the formalization of differential geometry, and then there's also this handful of people working on the formalization of algebraic geometry. And I would say, you know, like, I think that something that people would love to see that is still in its infancy is like, you know, a like collection, you know, following the Stacks project of just like, you know, everything done with a direct correspondence between the Stacks project and a lean library. I think that would be a beautiful thing to see. And, you know, people talk about it like, you know, projects get started. I think there's a lot of work to be done there, and I think it would be beautiful to have it done.
So like 56 separate projects.
No, there's very much an attempt to keep it all in the same project, and sort of part of the challenge is sort of that people really do debate to sort of set up the foundations in a way that are compatible. So maybe just as a tiny example of this, something that was not a ton of work, but that I was very proud of doing last summer was a project to write down, you know, using the sheaf theory library developed by the algebraic geometry people, the sheaf of holomorphic functions on a complex manifold. So the reason that I wanted to do this, even though it's not, you know, mathematically that hard, is just that it was going to be a test that the sheaf theory library developed by the algebraic geometers and the complex manifold, like, and the sort of abstract manifolds library developed by the differential geometers and the sort of holomorphic functions library developed by the analysts could all be like simultaneously used. Like somehow these projects are all being developed, you know, in the same, you know, folder on the internet, but, you know, you need constant tests like this by use cases that would involve all of them to check that even though they live in the same folder, to check that they actually can all be imported and used together compatibly. And so, yes, I was able to do this. Like I was able to, I think my test was to set up the sheaf of holomorphic functions on a complex manifold and check that if the manifold is connected and compact, then, you know, in fact, there was only like a one-dimensional set of global sections. So this was like a test that these three libraries worked together. And yeah, it worked fine. But I think it requires like constant effort and thought and dialogue to make sure that these things that are being developed do work together.
More questions? Please.
What's an area of mathematics which is like common but like glaringly missing in MATLAB, and why?
The question is about common parts of mathematics which are still missing from MATLAB and why.
Well, I mean, so for example, like as you've noticed, like the stuff that I've called differential geometry is very much sort of abstract theory of manifolds, like sort of the stuff you would do after that, you know, the Riemannian geometry is missing. And I don't think there's any obstacle in principle to doing it. It's more that somehow the people who were working on this chose to work on the foundations, like in a very general way, rather than working on the manifold theory. Then there are things that are missing because of the tastes of the people involved. So I would say, for example, that numerical analysis is missing. And, you know, it's a shame because there's lots of very theoretical numerical analysis that's theoretically very interesting. I think this is just a matter of taste. Like the people who have been attracted so far are not, you know, are not the sort of theoretical applied mathematicians who might be particularly interested in developing a theoretical numerical analysis library. But I mean, that's where recruitment problem.
Let me add that something which seems to be underrepresented is concrete examples of various things. You know, people seem to be happy with like 2 examples.
That's true. I actually, maybe one particular relevant example is that, so another big thing that I've been working on the last year is teaching undergraduate mathematics using this kind of software. And I really had this vision of the kind of course we do teach to undergraduates where everything that you do, like, you know, you don't just talk about the abstract theory of injective functions, you really do prove that the function, you know, x squared minus 2x is injective. It fails to be injective. You don't just talk about the abstract theory of prime numbers, you really do provide tools for them to be able to check for themselves that I don't know, 97 is prime. And so some of the automation, like for example, this kind of automation that I was talking about was partly motivated by knowing what we would need for differential geometry, but it was also partly motivated by trying to make accessible to undergraduate students the kinds of arguments that we do write on paper and that get involved in working with concrete numeric examples.
More questions? If not, let's thank Heather for. We're going to skip next week. And then on February 7th, we're going to have Jordan Ellenberg here in person to talk about his recent work with DeepMind on, you know, again, finding and proving conjectures using computers. So I hope to see you all there.